Math 1332, Chapter 3, Symbolic Logic, Section 5, Euler Circles, Video 6, a fourth example using Euler circles. This will be the final video in this series. I wanted to do one more because the last one kind of left a bad taste in my mouth. Not because it was difficult, but because it was more difficult than the others, and I want to end with one that's a little bit easier to follow. Full disclosure, this is the second take because I forgot to press record. Silly me. Determine if the following argument is valid. Sorry, I had to pause and undo some things I did in the first recording on the next page. Notice that this is a generic argument. Generic argument. Premise 1, all A is B. Premise 2, all C is B. Therefore, some A is C. Now, you can try to approach a generic argument by replacing A, B, and C with some specifics. For example, A is dogs, B is 4 legs, and C is cats. Premise 1 would be all dogs have 4 legs. Premise 2 would be all cats have 4 legs. Therefore, some dogs are cats. Now, you do have to be careful when you put a specific in for a generic because you may be influenced by the words. Clearly, dogs are not cats. So that conclusion can't obviously follow, can it? But remember, when you're studying the validity of an argument, you're not questioning the truth value of the premises or conclusions. Not at all. You're asking, must the conclusion follow logically from the premises if the premises were true? So be careful putting in words, or even if words are already in there, to go, well, that conclusion is clearly false, so this must be invalid. No, truth value and validity of an argument are actually independent things. Premise 1, all A is B. Premise 2, all C is B. Conclusion, therefore, some A is C. We clearly have 3 sets of objects, set A, set B, and set C. Don't have anything covered up here. All right, premise 1, let's see if we can illustrate it. All A is B. What type of statement is that? Well, it's universal and it's affirmative. It's a universal affirmative. And remember how we show a universal affirmative? We put one circle inside of another. So we will put the little circle inside of the big circle. And if we say all A is B, then the smaller circle has to be A. The larger circle has to be B. This successfully shows all A is B. Premise 2 is also a universal affirmative. All C is B. So just like before, we have to put the C circle inside the B circle. Let's make the circle a little bit smaller. And we'll call it circle C. Now here's where you have to be careful. I casually made an assumption which may force you into the incorrect decision at the end. Because the question now is, must the conclusion follow that some A is C? Well, keep in mind that, well, first off, some A is C is a particular affirmative. And a particular affirmative is 2 overlapping circles with the X in their intersection. Since this doesn't involve B, let's get rid of it for a second. Can we show the conclusion? The answer is yes. This picture shows the conclusion. But here's the problem. If you can show the conclusion, it doesn't mean the argument is valid. If you must show the conclusion, that shows the argument is valid. But a good way, again, to try to determine if an argument is valid is to try to show that it's invalid. That's easier. Try to break it. Now, how would we break it? In other words, what would have to happen for the argument to be invalid? Excuse me, what would have to happen for the conclusion to be false? Well, we would have to not be able to show that some A is in C, which means there would not have to be an overlap. So in other words, if we add something like this, then that would break the conclusion. That does not illustrate the conclusion. So, is it possible to show premise 1, circle A inside of circle B, premise 2, circle C inside of circle B, but not the conclusion needing circles A and C to intersect? So, can we put A and C inside of B without them intersecting? Well, with the circles you see, no, they're too big, but the size of the circles is actually pretty arbitrary. If I made this circle smaller and this one's smaller. Let's put A's label with it. This shows premise 1, A is inside of B. This shows premise 2, C is inside of B. Does this show the conclusion? It does not. The conclusion requires A and B to intersect. They do not here. Although it's possible to draw the diagram in a way that illustrates the conclusion, it is also possible to draw the diagram in a way that does not illustrate the conclusion. Since the diagram for the premises does not force the diagram for the conclusion, the argument is invalid and you cannot draw that conclusion.